Okay, I'm going to test the bit transformer now. First of all, the output is going to be the two secondaries, this secondary and this secondary, in series into a 456 ohm resistor here. So it's just going to be straight Ohm's law figuring out the output. I'll have the volts squared over the ohms will equal watts, and there shouldn't be any argument about the output. And just to show you, here's the here's what the ohms are. 456 ohms, okay. All I'm testing right now is the primary is going to be fed with 230 volts, and I'm using a Variac plugged into a 120 volt 60 hertz grid, and it feeds the low voltage side of a microwave oven transformer, and I only need 13 volts into that side, and I get 230 volts out here, these two wires, because the microwave oven transformer kicks up voltage quite a big ratio. So that's how I'm getting my 230 volts. Also, the high voltage side of this microwave oven transformer has very thin wires in it. So just so you know, when you see it's not drawing very many amps, maybe half an amp, it says, and that's the thickness of the wire, so for sure there's not a lot of amps going in here. Now I'm going to take the voltage, the voltmeter, off the resistor and put it over here of the output. Okay, so that's the 230 volts, and now I'm going to crank up the Variac until I get 230 volts. So here we go. Volts is in AC, 700 volts. So here we go. $47, $100, $211, $237, $230. Okay, 230 volts is going in here now. Let's look at the scope. If you don't use a scope on this, you won't know what's going on. Here is the amperage, the triangular. This is the voltage. Between here and there is the phase shift. And actually, the only time power is made is this triangular section here, because that's the overlap period of the voltage and the amperage. Okay, so when you measure this phase angle, it comes to 77 degrees. And the power factor of that is 0.22. Okay. I'm going to even this up. Right there. So between there and there is 77 degrees. From here to here is 360 degrees. Okay, so now I'm going to take these voltmeters and put them across this resistor so we know how many volts there are across the resistor. $196 volts. Okay, that's across a 456 ohm resistor. Okay, so hold on a minute. Okay, 196 volts times 196 volts divided by the ohms resistance is equal to watts. It's Ohm's law. And we have 84.2 watts. Not too bad. Okay, now we're going to look at the input. The input, we know it's 230 volts AC, times the amperage, which I'm going to show you here in a little bit, times the power factor. And you need to have the power factor because we're in AC and there's a phase shift between the volts and the amps. They don't just line up. The volts comes before the current. And you need to know the phase angle, and then you get the cosine, and the cosine is the power factor. In this case it happens to be 0.22. Okay, just 1 minute. Okay, let's look at the scope again. This is the amperage, the triangular one. It looks to me I'd say about 11 spaces. We're in the 0.05 square division. Sorry. See that? We're on 0.05 square division. That means each of those squares is 0.05 volts. And that means that each of those 5 spaces between inside of a square is 0.01 volts. Okay? So you can count. Like there's 10 from here to here. I'd say it's about 11 spaces, okay? Remember that. 11 spaces for the amperage. We don't have to worry about the voltage because we know it's 230. You know, actually I thought it was 196, but it was 146. So this is the real one. I'm sorry about that. Let's find out what the amperage is again. I thought that was pretty low. It looks like about 14 from here up to here. Maybe 15. Let's say, I'm going to say 14. 14 spaces, peak to peak, okay? Okay, remember there was 14 spaces we counted. It was almost 3 square divisions of 0.05, but it was 14 spaces counted. And each space was 0.01 volts because there's 5 of them in a 0.05 square division. So that gives you 0.14 volts peak to peak. Now if you want to figure out the AC amps, you divide by 2 because you don't want peak to peak. You want from the zero line up or down. So this is how you do it. 0.414 divided by 2 is equal to 0.07. Okay? Now you want to get RMS value. And the way you do that, you can ask any electrician who knows his stuff. You times it by 0.707 will give you RMS. Okay, so 0.07 times 0.707 is equal to 0.049 volts RMS. We're almost there to figure out the current. Now, there's a 0.1 current shunt, a resistor, in line with the scope probe measuring the voltage. So what you do is you go, for the final tally is 0.049 divided by 0.1 is equal to 0.49 amps. Okay, that's the amps. 0.49 amps. So up here you can put in 0.49. Okay, we're almost there, but we need to know the power factor. It's very important because the volts are not right on top of the amperage. There's a big shift, and it's only during overlap that actual power is made. So now let's look at the phase angle. Phase angle means the difference, the distance between the volts and the amps on the scope. I guess you could call it that. Okay, wait a minute. Okay, here we go. 197, 196 across the resistor, okay? Now, give you a little education if nobody knows about this. Voltage is this here. Here's the amps, the triangular one. Let's get the amps centered. Okay, the volts looks almost centered. Okay, so now what you do is you count from 360-degree cycle, one cycle of AC. That's from here to here. 28 spaces, I already know this. 28 spaces. Okay, so now you divide 360 by 28 and it tells you what each of those little spaces is in degrees. Okay? And now you go and you count from, see that's from here, 1, 2, there's 5, 6, I'd say it's about 7. I've done this before and it was 7. Another guy, I took a photo of this, he did it all, he agreed with me. 7 spaces, 28. And this comes to 77 degrees phase shift. This is right here. Okay. And that has a cosine of 0.22. Okay, so 1 minute I'll show you the math. Okay, I'm back here, 196 volts across the resistor. And I'm going to look at this because I can't believe what I just got. If that's 7 spaces, I'd say it's 6. 6 spaces, okay? 6, not 7. If I did 7 spaces, 28 spaces is equal to 360 degrees, okay? If you count it, you know, one AC cycle, how many of those little spaces are there? There's 28. 360 divided is 12.85 degrees per space, okay? 7 spaces times that comes to almost 90-degree phase angle, which is like crazy. And 6 spaces is 77 degrees. That's what I had before. That's what my friend who knows everything about scopes and phase shift, he says, yeah, it looks to him like 77 degrees too. So I'm going to go with 77 degrees. Now you just go and Google what is the cosine, C-O-S-I-N-E, of 77 degrees, and it is 0.22. And your cosine is your power factor. Okay? And now look what the input is. Wow. Only 24.79, okay? Now, if you're wondering what I'm talking about, I think I showed this before, but see the voltage and see the amps. And here's the 0 line. And it's AC, so there's down here and there's up here, okay? This triangular portion, the overlap period, you don't have power unless there's volts and amps at the same time. And you don't have power unless there's volts and amps at the same time. And so the only time real power is being made is right here. So that's why you want to know the phase shift, the phase angle. Okay, one more thing. This is a triangular. It's not really sinusoidal. It's not nice, smooth looking. That's because the core is saturating. Same with this here. The core has been saturated, and it's being saturated on very little amps. And because it's saturated, you're making a lot of power. Okay? And it should not be saturated because it usually takes a whole bunch of amperage to saturate a big core like this thing. So that shows you that these shunt bars are doing their thing. They're taking the back EMF, which normally goes into the primary, and is shooting it back over here and colliding and annihilating it as it comes this way and this way and this way and this way. Shoots backwards, you know, back EMF, forces magnetic. So my theory, some of it is being annihilated by a collision, both going the same directions. Some of it gets through and reinforces the secondary. and it's supposed to come through and reinforce the opposite secondary instead of going here. So power that normally raises your draw instead goes and boosts the power of the opposite coil, and it goes both ways, okay? So this is dependent upon people understanding phase angle with AC power. But, you know, that's okay. It's what it is, and any good electrician will tell you that's what it is. So, I guess, oh, let's talk about these. These are additional power to be made, and you don't want more coils around that shunt bar, and you don't only want to do this in here, because if you do it full length, it collides and it just cancels out. You don't get anything. But you can pick up power over here and over here. You should divide it like thirds, only have wraps here and there. And I haven't really tested much with this yet. I'm still just working on the basic bit, but this is something that normally people don't do, and it might be worth maybe 10 watts or so, maybe 20, maybe 5. But this is additional stuff. The shunt bar winds. Okay, so anyways, output 84.2 watts, input 24.79. Not too bad. Okay, thanks for watching.